When you watch a standard generative video model track a walking pedestrian, the output appears flawless. But the moment the camera pans away to observe a nearby building and then snaps back to the original subject, the illusion breaks. The pedestrian is frozen in place. Foundational video generation architectures lack a structural understanding of object permanence. Out of sight literally means out of mind. Existing memory mechanisms process simulated environments as static canvases. They excel at memorizing and reconstructing motionless backgrounds based on geometric overlap. But the physical world is populated by dynamic subjects governed by independent kinematics. When a moving subject exits the camera's field of view, current models lose their latent representations. Upon re-entry, the system renders them as frozen statues, distorted phantoms, or simply lets them vanish into the background. Simulating the physical world requires a model to implicitly calculate a subject's unseen trajectory while the camera looks away. Without this continuous tracking, the generated sequence unravels into disconnected frames. The technical bottleneck lies in the structure of standard diffusion latents. In these representations, the ego motion of the camera and the independent motion of the subjects are heavily entangled. Mapping camera poses to a fixed 3D space is sufficient to anchor static elements like roads and buildings. It completely breaks down when applied to kinematic entities that continue to move independently of the viewport. To bridge this gap, the researchers proposed a framework called hybrid memory. Hybrid memory demands dual functionality from the model. It must act as a precise archivist, perfectly reconstructing the immobile background grid. Simultaneously, it must operate as a vigilant tracker, predicting the forward momentum of dynamic subjects, entirely independent of the camera's perspective. These two streams of logic, spatial reconstruction and kinematic prediction, must process in parallel without overriding one another. Without explicitly decoupling ego motion from subject trajectory, generating long horizon video with complex camera movements inevitably collapses into spatiotemporal chaos. At the structural level, we operate within a full sequence diffusion transformer, or DIT. Its objective is to predict highly accurate target frames based on a sequence of historical context frames. The naive approach to memory retention is brute force, taking the entire sequence of historical latents and injecting them directly into the current generation process. This introduces overwhelming spatial noise, flooding the model with irrelevant data from static backgrounds. This indiscriminate data flood obscures the vital motion cues needed to track moving subjects. It misleads the model's reasoning pathways and exponentially inflates computational costs. To track hidden subjects without crashing the system, the architecture requires an aggressive, highly targeted retrieval mechanism that filters data before it ever reaches the attention layers. This filtering begins with the first phase of the HyDRA framework, the memory tokenizer. The tokenizer takes in the raw, uncompressed memory latents from the historical context frames. These latents pass through a 3D convolution layer with a 2x4x4 kernel. It sweeps across the data, expanding its spatiotemporal receptive field to capture long-duration motion. The spatial grid compresses, temporal layers weave together, outputting a compact array of memory tokens, prioritizing essential motion cues. These tokens feed into the second half of the framework, dynamic retrieval attention. This module directly replaces the standard 3D self-attention layers inside the DIT. We establish opposing inputs. Target frame latents act as queries, while memory tokens serve as keys and values. The system calculates an affinity metric via an element-wise spatial product between them. Tokens illuminating with high scores represent an exact spatiotemporal correspondence to the hidden subject. The model then executes a top K retrieval. It isolates only the handful of memory tokens with the highest affinity scores, pulling the crucial motion cues forward while discarding the remaining data. However, injecting only historical data at this stage would destabilize the local generation of the current target frame. To maintain structural integrity, the system concatenates the retrieved top K tokens with the keys and values drawn from the target frame's immediate local temporal window. Finally, the module runs standard softmax attention across this curated hybrid data block. By mathematically seeking out specific motion cues rather than relying on passive coordinate data, the attention mechanism allows the model to seamlessly pick up a hidden subject's trajectory exactly where it left off. Proving this capability requires a highly specific testing environment. Natural internet videos almost never contain perfectly captured, unoccluded sequences of subjects exiting and re-entering the frame. To solve this, researchers constructed HM-World. It is the first large-scale video dataset explicitly built to evaluate hybrid memory, featuring 59,000 synthetic clips procedurally generated in Unreal Engine 5. The critical design feature of this dataset is the deliberate decoupling of camera trajectories from the actual subject paths. The clips feature scripted back-and-forth camera panning. This active motion forces subjects to slip into the unseen margins before re-emerging, ensuring a dense volume of hide and reappear dynamics. Evaluating these events required a novel metric, Dynamic Subject Consistency, or DSC. The DSC methodology uses YOLO bounding boxes to crop moving subjects out of the predicted video. It then passes those regions through a pre-trained clip model to extract semantic features, calculating their similarity against the ground truth video. Standard pixel-wise metrics, like PSNR, evaluate entire frames, making them blind to precise kinematic errors. The decoupled HM-World dataset, paired with feature space comparison, provides a rigorous benchmark for spatiotemporal coherence. This bar chart displays ground truth dynamic subject consistency. HyDRA achieves 0.849, stepping significantly ahead of context as memory at 0.839 and default at 0.826. It also outperforms the zero-shot capabilities of advanced commercial models like WorldPlay. The runner-up approach, context as memory, filters context based on field of view. It fails in complex dynamic scenes because it relies entirely on overlapping static geometry. HyDRA succeeds because its query key affinity matrix evaluates semantic motion features rather than just spatial coordinates. It predicts where a moving subject should be, rather than just recalling where it was. This capability translates directly to downstream applications. In autonomous driving, a vehicle must maintain a persistent internal model of unseen pedestrians to anticipate their reemergence. Accurate out-of-view extrapolation is mandatory for training embodied intelligence and robotics to operate safely in chaotic environments. By engineering structural object permanence into the latent space, video generation moves closer to the continuous spatiotemporal coherence required for effective world models.